In these next several videos, we're going to work some examples from our spiral and learn how to solve some differential equations that are what we call separable. Before we do an example though, I want to just say something about something I kind of glossed over in the last video. If we go back to this equation, y prime equals 2x plus 5, remember there's different types of notation, and that y prime is the same as saying dy dx. So when we go to solve this, when we integrate this, the first thing that we would really do here is we would actually multiply both sides of this by dx. And I think I just kind of glossed over this fact in our last video. So we end up with dy equals 2x plus 5 times dx. So when we get to that integration step, here's why this is important. When we integrate on both sides of the equation, what we're really integrating on the left-hand side is 1 times dy. So that's how the left-hand side becomes y. So we're integrating the function 1 with respect to y. On the right-hand side, 2x plus 5 is going to still be x squared plus 5x plus c, since we don't have limits of integration. So we discussed that one in the last video. I just wanted to kind of firm that up. So looking at page, I believe that we're on page 115, we're going to talk about separable differential equations, and we're going to work this first example through. When we get to the second one, I'm going to ask you to try to pause the video a couple of times and work through without me. But let's just do this first one together. All right, so we are asked to find y equals f of x. So we're finding a function of x, and that's going to be called y. We're told it is the particular solution to dy dx equals x times y. So again, we're not finding a general solution, but we're finding a particular solution. And in order to do that, we need an initial condition. So this 0, 5 right here, that is our initial condition. And for the function y that we find, 0, 5 must be a point that satisfies that function. So the first thing that I'm going to do is I'm going to just rewrite my dy dx. So dy over dx equals, and we said that's equal to x times y. That's my cat in the background. Oops. All right, and again, we want to move that dx over to the other side, and we can do that with multiplication. So when we multiply, oh my goodness, when we multiply both sides by dx, we're left with dy equals x times y times dx. Okay, so we're ready for the first step. The first thing that we want to do is we want to separate. So what I mean by that is we want all of the x stuff on one side of the equation and all of the y stuff, so to speak, on the other. So if I look at the right-hand side, this is why we always multiply by dx first. I can see that dx is on the right-hand side of my equation and dy on the left. So that means I need to move algebraically y to the left-hand side. So we can do that with just division. So that's going to be our first step. We're going to separate. All right, so we can do that by just dividing by y. So when I divide both sides by y, I could rewrite this as 1 over y dy equals x dx. So all we've done so far is manipulate this equation, this differential equation, so that we can separate all of our x junk on one side and all of our y junk on the other. All right, step 2 is going to be to integrate. All right, so as we integrate, we're going to integrate both the left hand and right hand side. Oops. Oh my goodness. All right, so 1 over y dy. We're going to integrate that, and we're also going to integrate x dx. All right, so we've got to remember those integration rules. When we integrate 1 over y, that's just the natural log of the absolute value of y. And we don't really need a plus c there. We are going to end up with a plus c on one side. If you're wondering why we don't need 2 plus c's, like one on the left and one on the right, is that like eventually when we go through a process of combining like terms, that unknown arbitrary constant, like that's going to get combined with something else, so with the other c. So since we don't know what c is, we don't need 2 because they just become one constant later, if that makes sense. All right, then on the right hand side, we're integrating x dx, so we know that's just going to be 1/2 x squared plus c. So I would just continue to put my c on the side with the x. All right, so that is the process of integrating. So those first 2 things have to be done in that order. The next 2 things that we're going to do, sometimes it makes sense to solve for y first. Sometimes it makes sense to solve for c first. But let's just back up for a second. Go back to the question. We are asked to find y, a function of x, which we have started. When it says find y equals, that means get y by itself. So we are going to have to isolate y, so we still have that to do. And we need it to be the particular solution to the differential equation. So we have to find a value of c so that the solution we come up with will pass through the point 0, 5. So for this one, I'm actually going to solve for y first because there's some algebraic topics I want us to talk about as we do this. So from step 2, we're gonna solve for y. I will tell you, as a general rule though, I would actually more often find c first, but on this one, let's solve for y first. So if I have this equation, the natural log of the absolute value of y equals 1/2 x squared plus c, I know that I need to exponentiate both sides with the base of e first to get y by itself. I'm going to be super lazy. Do as I say, not as I do. I'm going to be lazy and just kind of do it over here in this equation. So all of this stuff will be our exponent on the right side. And we know that on the left side, e and the natural log will kind of undo each other. So on the left-hand side, we're left with just the absolute value of y. So through the process of exponentiating base e, we've eliminated the log with the base e. On the right-hand side, we now have e to all that junk. So 1/2 x squared plus c. So this is important. The c is in the exponent because we exponentiated the entire side of that equation. So from here, a couple things we can do. Before we deal with the absolute value, let's just like out to the side, remember real fast our rules about powers. So if I have, for example, x squared times x cubed, I know that when I multiply 2 powers with the same base, that I can rewrite that as a power and I can add the exponents. So I keep the base and I add the exponents. So we're actually going to go backwards. If we look at the right-hand side of the equation and we see that e is raised to the power of 1/2 x squared plus c, I could really break this into the multiplication of 2 powers with the same base. So I'm going to keep my absolute value of y, but this is going to be e to the 1/2 x squared times e to the power of c. So it's just, instead of following this rule from left to right that we just went over, we're really going from right to left and saying that like, hey, if I can think of this as, let's just look at it this way, x to the 2 plus 3 power, I could break that back into x squared times x cubed. Same thing, but we're doing it with c. So because we have two terms on our exponent, we can rewrite it as a product of two powers. All right, let's think about this. C is just some number that we don't know what it is. So e to the power of c is still just some number, and we just don't know what it is. So what I can do now is I can get rid of e to the power of c and just call that c, because c stands for some arbitrary constant, a constant of integration, and it's just a constant number. So I can put it out in front. So I have c times e to the 1/2 x squared now. So lastly, when we want to get rid of those absolute value bars, let's just think about a simple example. So out here to the side, if I had the absolute value of x equals 4, for example, that means that I would want x to be any number whose absolute value is 4. So the way that we often solve this in algebra is when we remove the absolute value bars, I have to consider both the negative and the positive solutions to that, to 4. Or sorry, to the absolute value of x equals 4. So that would be a -4 or a +4. We often write that as plus or minus 4. We could do the same thing over here, but again, stop it, you already ate. Again, we've got to keep in mind that like c is just some number we don't know. So if we remove the absolute value bars, we could write this as plus or minus c times e to the 1/2 x squared. But again, like it doesn't matter if c is positive or negative because we don't know what c is. So in this case, the way this one works out is we can actually ditch the plus or minus and just say that y equals c times e to the 1/2 x squared. Because what will happen is when we solve for c, that's when we will discover whether c is positive or negative. So I don't really need to consider both equations. All right, so we've solved for y. We've isolated y, but we still, oh my gosh, oh my God, I'm so sorry. My cat is going crazy. Boomer, calm down. I'm not editing that out. Sorry, I've been recording too long. All right, we're gonna plug in now this initial condition, 0,5, and we're gonna now figure out what c is. So let's do this last step. So I'm gonna plug in 0 for x and 5 for y. So 5 equals some number c times e to the 1/2, oh my God, 0 times 0 squared, shh, boomer. So 5 equals c times e to the 0 power. So 5 equals c times 1, because anything to the power of 0 is 1. So lastly, 5 is equal to c. So we're not done yet. The very last thing that we have to do is just rewrite that with the 5 in it. So we know now that it is in fact a positive 5. So our final answer is that y equals 5 times e to the 1/2 x squared power. So going back, let's make sure we did everything we needed to do. We found a function y in terms of x. Y is isolated, and it is the particular or specific solution that passes through the point 0,5.